All right, Calc 3 people, I apologize. I have a feeling this video is going to go well past 25 minutes, but we'll see. It's important to get it all out at once though, and so I'm gonna push through it. And yeah, I apologize beforehand if that's the case. So let's get right into this. This is our fifth video. Today is the 3rd of September. And we're now getting into integration of vector valued functions and the arc length parameter, which is really important for stuff that's coming up theoretically. So okay, here we go. Let's make a definition here. As I keep saying, we're really not doing anything new. All we've done is thrown some vectors in there, but it's stuff we know already, right? So if you take a vector valued function, r of t, and you integrate it with respect to t, then you get an antiderivative function with a constant, only now the constant is a vector, right? And sure enough, if we were just working with one by one vectors, right, constants, this would just be Calc 2, okay? So here we go, so how about this? Let r of t equal x of ti plus y of tj plus c of tk. Right, so now I have some function x of t in front of the I, y of t, and if I take the integral of r of t dt, this is just going to be the integral of this guy times I plus the integral of this guy times j plus the integral of this guy times k. And these ij's and k's are not inside the integral. You're not integrating ij or k. Those are just components. So it's exactly as we've been doing. And now you just go piece by piece. Okay. So here's one of those awesome real world math examples that sort of, I don't know, gets us to where we want to go. So we're talking about hang gliding. So we know a hang glider is accelerating. So this hang glider is flying around, is accelerating at this function. It's minus 3 cosine t I minus 3 sine t j plus 2k. I don't know how we found this, but we did. We figured out, we don't know its position function, but we know its acceleration, this hang glider. Okay? We have an accelerometer that measured it. The initial position, takeoff, of the glider is the 0.300. So at time equaling 0, we're over here at 3i. Okay. All right. We also know that at time 0, the velocity is 3j. So it's going in the j direction at at this rate, which is 3. Okay. So what we want to do now is find the hang glider's position function. R sub t. Okay. No, really what I want to do here is give you this function, integrate it twice, and figure out with these initial conditions how we're going to find a solution, right? So this is actually an initial condition problem. R of 0 is 300, and V of 0 is 030. And these are actually vectors, so I should have vector notation there. Right? Okay. So first let's integrate this a function to get v. So v sub t is the integral of a sub t dt, which is the integral of minus 3 cosine t I minus 3 sine t j plus 2k dt, which turns out to be the integral of cosine is sine, so I have minus 3 sine t I. These are all vectors, sorry. The integral of sine is minus cosine, so I have plus 3 cosine tj plus 2tk plus some constant vector I'm going to call C1. Okay. Now, I got new pens, 6 of them, and my favorite color purple is in here. Okay, so here's our initial condition for the velocity. The velocity at time 0 is equal to the vector 3j. Okay, so we have the velocity at time 0 is equal to 3j, which is equal to minus 3 sine of 0 I plus 3 cosine of 0 j plus 2 times 0 k plus the vector c1. And this says, am I still on there? Yeah. This says 3j equals, this should be a vector. Okay, 0 plus 3j plus 0 plus c1. And this says c1 is the 0 vector. Okay. So now we're going to rewrite this v as minus 3 sine ti plus 3 cos tj plus 2tk, because we showed c1 is 0. Okay. All right, now we're going to go integrate once again to get r. So r is the integral of this guy, which is the integral of this. Minus 3t sine I plus 3 cosine tj plus 2tk dt, right? And when you integrate sine, you get minus cosine, so that makes this positive. So you get 3 cosine ti plus 3 sine tj plus t squared k plus another constant from this constant of integration. Okay. Now, so that's r of t. We know r of 0 is 3, 0, 0. So, so what do we do here? So we have on the right hand side here we have 3i plus c2 equals 3i, which tells me c2 equals 0. Okay, so now here's our function. It is 3 cosine ti plus 3 sine tj plus t squared k. Okay. I gave a homework problem where it's the exact same thing as this, but But C2 or C1 or both are not 0. So it's a little different. But you get the idea now. All you do when you integrate is you pick up these constants, which are vectors, and you still have to put your initial conditions in to get your final solutions. Okay. So in the next section, which is really the precluder? Yes, to 13.4 and 13.5, which are a big deal. So 13.3 is really about some theory that we need. It's a really interesting section, and it has to do with arc length. Now, some people in Calc 2 skip arc length. Sometimes, some semester, it's one of those optional things you can do as a application piece. Sometimes I do it, sometimes I don't. Sometimes I spend more time on center of mass, sometimes I don't. But here, arc length is important. So let's go back to the function, which has components x, y, and z. Right, so x, y, and z are the component functions of this function r. Okay, and now the parameter actually has to have endpoints. Otherwise, when you're talking about arc length, if one of the endpoints is infinity, the arc length is infinity. There's nothing to do. All right, so now we're saying, if I limit this to 0 to pi or whatever, minus 1 to 1, what's the length of the arc? And now we're working in 3 space. Okay, so I prove this in every class I've ever taught. It's the same thing. You just take the derivative, so x prime of t squared plus y prime of t squared plus z prime of t squared, oops, that shouldn't go there, dt. Okay. All right, where's my purple? So excited about these new pens. Given this vector r, which has x, y, and z as components, if you look at this square root, this is actually the norm or the length of the derivative, where v is dr dt. Okay. So if you really want to clean this guy up, it's a definite integral. You go from a to b. You can actually write it like this, and that's really sweet. It implies, you know what you're doing, right? Because if you take this function r and you compute v, you get x prime I plus y prime j plus z prime k. And then if you take the length of that guy, you square each of the components and take the square root, and that's what this is. So there you go. Now this is a really compact way to write the arc length from a to b of the function. Is that 2? That's 2. Okay. All right, let's get into the meat of this thing. We're at 13 minutes. Oh, I'm doing good. All right, so this is page 3. Okay. All right, so I'm really focused now. So we're gonna let C be a curve in 3 space, which is parametrized by t. So we're working with the time variable here. And so as we go through, each t maps to some point p sub t, which is just x, y, and z, right, on C. So as this vector is running through, as this t is running through its parametric interval, at each point it's giving you a p, and this makes a curve in 3 space, right? This also gives a directed distance which is a difficult thing to grasp. And this directed distance is defined to be s, which is a function of t. Okay, and this t naught is the starting point of the parametric interval of the curve. Well, of the curve we're looking at, right? So we're starting at t naught, we go to t, and we're gonna plug in to this vector v. We're gonna use a dummy variable, call it tau. And then we're integrating with respect to tau, okay? Now, if t is bigger than t naught, so this guy is bigger than that, it always will be. This function, s of t, is the distance along the curve from p sub t naught to p sub t. And so this is so weird. Okay, so this is key though. This is a key point that we need. Each value of s, and again, s is an integral, determines a point on C. So we get another parameterization of C. And S parametrizes C with respect to S. Okay? Not T. So T is our time variable, but S is our length variable. So what we've done is we've parametrized the curve. But instead of using T as our parameter, we've now used S using this function. All right, and so now we define S this way. We call S the arc length parameter. If you have a lot of questions about this, I understand. I do still. Took me a while to get my head wrapped around it, but when we're in this guy here, we've parametrized the curve with respect to t, and t is just time, so it's moving through. But with this guy, we parametrized the curve with respect to s, and that's different because each length s is different for every curve, but it's normalized to the curve itself. Okay? All right, and this helps tremendously. With twists and turns. Which isn't very mathy, but next week you'll understand. Okay, so if we apply this to what we have already, this S function, which runs from t naught to t, is really this. It's x prime of tau squared plus y prime of tau squared plus z prime of tau squared d tau. Just rewrote it. And this equals the integral from a to b, v of tau d tau. So the length of v of tau. This is supposed to be a tau d tau. Okay. I'm doing pretty good on time. Here. Okay. So, the FTC, there's only one way to write it. We know that. The FTC tells us that ds dt is the speed, right? Okay. We also know that v is the derivative with respect to t of the position function. Here's page 4. Still on there? Yep. So we know this vector v was equal to dr dt, and we know ds dt is the norm of v. So we're going to put these two together. Okay. And this vector v is tangent to the parametrized curve in the first place. Okay. And we're going to let cap t be the vector you get when you take the velocity vector and normalize it. Okay. Now this guy turns out to be very important. Okay. So this is a tangent vector of unit length. So what do we call it? We call t the, I should make it capital, the unit tangent vector. Okay, capital T, the unit tangent vector. All right. So, more theory. It's weird because I taught this enough times to know, like, I normally blew off this S parameter, and then I'd get to 13.4 and 13.5, which are a big deal as far as sections go. And they're super cool because you talk about planes and the TNB framework, all that stuff. And without S being well developed, which is what I'm trying to do here, doesn't make any sense at all. Okay, so we're gonna go back into R2 to get a handle on what the hell's going on here. Okay, and we're gonna consider the unit circle, which we're going to parametrize by this position vector. R sub t is cosine ti plus sine t j. Okay. And here we are in the x1, x2 plane. Okay, well if t is 0, so when t is 0, I have I. So here's R of 0 right there. When t is pi over 2, I have j. When t is pi, I have minus I. When t is 3 pi over 2, I have minus j. And then I come back around. So here we have our unit circle traverse counterclockwise. Mine's going to look like a football, but there it is. A sloppy ellipse. Okay. So there's R. And we're going, so this is directional now. We're going this way. You can also parametrize this going clockwise, or you can sort it at pi over 2. There's lots of ways to do this. Okay. So let's just let t be, t goes from 0 to 2 pi. We're going this way. Okay. Now let's look at the velocity vector here. It's minus sine ti plus cosine t j. Okay. Now the length of this guy is 1, because sine squared plus cosine squared is 1. So this guy is already equal to t. Right? It is the unit tangent vector at any point along the curve. Okay. Now at t equals 0, little t equal to 0, I have this. Okay. So if you plug in 0, you get j, which is, this is j. Okay. If you go to t to the pi over 2, you get minus I, which is this. All right. If you let t be pi, you get minus j, which is this. All right. And notice each one of these lengths is 1. I've actually made it match the graph. Same here. We're going to get a vector of length 1. So as we go around, we have this unit tangent vector, and it never changes length because it has no magnitude. That's the beauty of it being length 1, being a unit vector. Okay. So v sub t is the instantaneous rate of change, the derivative of r of t with respect to t, the time variable. Okay, and here's where this gets really intense. We're almost done, so stay with me, please. If we were in class, I'd be throwing stuff at you. I'm sure you're wide awake. All right, page 5. We rarely get to 5. Here we are. Okay. So this vector v up here, which in this case is actually cap t, but it doesn't matter. It's the rate of change of r with respect to t, but little t being time. And what we want to know is, here's my question. How does r of t, let me put r, how does the position vector r change with respect, God damn it, stay still, with respect to to s, the arc length parameter, okay? In other words, what is dr ds? Okay. Using the chain rule, dr ds is going to be dr dt times dt ds. Remember this? Chain rule, right? Okay, if we rewrite this, we have dr dt over ds dt, right? But right here, we're saying dr dt is v of t. And up above somewhere, we have that ds dt is the norm of v, and that's just t. Okay? So here's the takeaway. I'm going to use this a bunch in the days to come. Dr ds is t. All right. Okay, so here's the rest of homework 3. So from section 13.2, I only assigned one problem, problem 15. And for 13.3, I assigned 6, 13, and 18. And I want you to get comfortable using GeoGebra. So when you do these problems, 6, 13, and 18, maybe even 15, just check it with GeoGebra. Have a look and see if you can get it to work out. All right, I only went to 29, so that's pretty good. I wanted to make it, under 25. I knew I was going to go over. And if I keep talking, I'm going to make 30. But I came in under 30, so that's good. See you all in a bit.